solve a problem, which is a sequence detector using more FSM, finite state machine. So here the problem asks us to design a 0-1 non-overlapping sequence detector. So here we have the sequence, which is 0-1, and it should be non-overlapping. And we have to do the following steps. So we have to draw the state diagram for this machine. We have to draw the state table, and then we have to find out what are the Boolean equations using JK flip-flops. And I will use a LogicAid here to get these. And finally, we have to simulate the circuit on Logisim-Evolution using an 8-bit shift register. So here the shift register will be the input to our circuits, which we call input X here, the serial input. And this serial input can be any random number, which should have, for you to test this, you should have some 0-1s in the input to see if your circuit will detect this sequence. Given that we have this 0-1 non-overlapping sequence detector, it means that given a sequence, for example, a serial input X with like some random inputs, we have to detect every time there's the sequence 0-1. So for example, here we have 0-1, we have 0-1, and we have 0-1. So it means that in our output, which is Z, we should have always 0, except when we detect the 0-1. So here it will be similar to the input, so all zeros except when we detect the 0-1. So this is the aim of this problem. So how can we design a circuit to give us the following outputs? First, we have to realize or know how many states we need to achieve this. So given that we are using more, we can say that, so we have a 2-bit number, so 0-1 is 2 bits. So it means we're going to have 3 states. So state 1, and we can call it state 0, is when there's no 0 detected. So this is always like the initial state. State 1 is when we have a 0 at the beginning of the sequence, so we can say 0 detected. And the third state, state 2, is when we have 0, 1 detected. So these are the states we care about to be able to detect this sequence. So this we can call S1, S0, sorry, and then S1, S2. And of course, S2 is the sequence, or sorry, the state where our output, so the output Z, will always be 0 except when it's in state 2 because we have the sequence that we want. So we can define our state diagram. So we can draw it now. So we have 3 states, S0, where the output is 0, S1 output also 0, and S2 is the output 1. Now, when we are in S0, we have no 0 detected. Let's say the next input is 1. If the next input is 1, it means we will only loop in our back to the states, because the next state is when 0 detected or 0, 1 detected. However, when the input is 0, so we have a 0 in the input, it means a 0 is detected, so we can go to state 1. Then in state 1, if again, we have another 0 detected. It means we will loop in the same state, right? Because this is the state when a 0 is detected in the input. However, when the input is 1 and we are in state 1, it means we have detected a 0 and now we detected a 1. So we can go to state 2. Now, if we have the input after this, so we have 0, 1, the input is 0, so we detected a 0, we can go back to state 1. But if the input is 1, that means we have to go back to the first initial state here. Because we need 0 to be, the sequence is 0 and then 1. So we need to first detect a 0 to be able to have the sequence. So this is the state diagram using Moore machine. Now we can draw the state table, so it's based on this explanation at the top. So here in the Moore machine state table, we just have the present state, and then the next state, and we have when x equals 0, which is our input, and x equals 1. And we have the output. Now I used 2 bits to have simpler explanation, but this applies similarly to higher number of bits or higher number of sequences. So the present state we have S0, S1, S2, and we know the output is 0, 0, 1 for each state. Usually the output corresponds to the present state. And for the next states, we know that when S0, x equal, at S0, x is equal to 0, we go to S1. However, if it's 1, we stay in S0. S1, x equal to 0 is again S1, and 1 is S2. And then at S2, if it's 0, we go to S1, and if it's 1, we go to S0. Now with the state table, we can get the JK flip-flop equations, which is the third part of the problem. So I'll use LogicAid for that, and then I'll show you also how to draw the circuit on Logisim. So now I will use LogicAid to get the Boolean equations. So I'll input the state table that I have. I have 2 state columns, 1 input variable, 1 output, and the length of state name I'll use 2, so I can put the 2 characters for S0 and so on. Put enter names. Oh, we also have to do this again because I didn't choose the Moore machine. That's pretty important. So here I have to press Moore machine. And I'll put X as the input and Z as the output. So the present state as 0. No, let me copy this from the table. S1, S0, 0. So this is exactly the same as the state table we concluded. S1, S0, and 1. Now we can press routine. So actually it shows you in LogicAid that you have to put the present state as the first column, and then the next state when x is equal to 0 is the second column. The third column is when it's x equal to 1, and the last one is just the output. And here it just writes what input variable you have on the side. So routine, flip-flop equations, I'll choose JK, sum of products, and these are the equations that I get. So now let me go to Logisim and design these circuits. I can copy this in a text here. So these are the equations. So for this, I need two flip-flops. So you see I have Q1 and Q2. So I can go to memory, JK flip-flops. And they will be synchronous, so I'll use the clock. Same clock for both. And I'll just make this in a tunnel. Clock. So I connected all the clocks together. Now let's see what is X. So X is our input. We know that Q1 and Q2 is the output of the flip-flops. So this is Q1 and then Q2. Now we need to know what is going inside J and K, which is given in these equations. So here I have J1 is connected to X. So I'll put X as a tunnel for now. And K1 is connected to 1. So I can just use a constant here. And then we have J of Q2 is not X. So this J is basically not X. So I'll put X here with the not gate. And the K is just X. So I'll just put the X directly. Now it's blue lines because X is not defined. And we will do that later. And then finally the output is just Q1. So Q1 is our output. And I think it's easier to connect it to an LED light. So when it's 1, it will just light up. So I can go to the output and choose LED light. And this is, let's call this set. Now what we need, so here we were lucky that none of the, like we don't have any combinational circuits. So, oh, actually here we do. So actually J of Q1 is X and Q2. I did not see this. So this is X, Q2. So for this, we need a circuit between X and Q2 and inside an AND gate. I can put this a bit here. And then Q2. So Q2 is not used in the output, but it's used inside the circuit to find the J in Q1. Okay, so now our circuit is complete. We just need to define our inputs. So this is the output, which is the sequence detector. So if there is sequence 01 passes in our input, this should be 1. And this is the circuit or the machine that is doing the sequence detection. And this is the clock for the whole thing. Now we need the input. And for the input in the question, it's said to use an 8-bit shift register. So we can get the shift register from the memory folder. So we have this shift register, and number of stages is already 8. So we have here 8 bits. Now we need, for the register, we need the same clock here where we have the triangle for it to also shift. And the last pin here will be our X. So basically the pin, the number that is at the last input last bit here is basically the X. So at the moment it's 0. This is why it's dark green. And we can try now to simulate and just auto tick enabled. Now you see when I simulate, I'm having question marks here. So the shift register doesn't know what should be, when it's shifted, what values to put next. So you have to put here, for example, in my case, I want to just put 0. So I'll put a constant in the first bit here. I want it to be 0, not 1. So every time it shifts, it's just going to give 0, 0, 0. Now, X here will be 1, 1, 0. So there are no, so here you see that if I press 1, so our sequence is 0, 1. So here I have 0, and then I have 1. The light should be on. So let me put it again. So I can put, for example, 1, 1, 1. Here I have 1, and then 0, 0, 1. This should be on. Here 1, 0. No light should be on. So you see the idea is that when I have 0, 1, so here X is 0. Now it's 1. So the sequence is detected. Can have a lot of ones here, for example. Again, there is 0, 1 sequence. After the 1, it should be detecting it. Then the light should be off. So this is how the circuit, a simple sequence detector, works with the shift register as the serial input. So this is the serial input, our X. So this is the one that it goes either 0 or 1, which we have in the next state column. And this is the circuit with the flip-flops, and this is our Z output.